Now we have got this curve on the x-axis of which we have the wavelength in micrometers, and on the y-axis of which we have got this spectral emissive power. You can see that spectral emissive power is written as E lambda or EB lambda, and it has got units of watts per meter square per micrometer. Watt per meter square means these are the regular units of E, and since we are talking about the spectral emissive power per unit of wavelength around a particular wavelength, so therefore we have got another wavelength in the denominator. Now what is this curve about? You can see those isotherms 50 Kelvin and 100 Kelvin and 300 Kelvin, 800, 1000, 2000, 50, 800 Kelvin. So at room temperature, if it is, let's say, 25-27 degrees Celsius, so that object would be at a temperature of 300 Kelvin. And 5800 Kelvin is said to be the temperature of the outer surface of the sun. So now we will see what this graph is about, what this chart is about. See, if there is an object at 27 degrees Celsius at 300 Kelvin, what radiations does it emit? It emits the radiations that have got wavelengths from 2 micrometer to 4 to 10, 20, 40, 60 and 100 micrometers. And if you recall, what was the range for visible light? The range for visible light was from 400 to 700 nanometers, means 0.4 micrometer to 0.7 micrometer. This is what is shown over here. So 0.4 to about 0.7 micrometer we have this visible light band. So this would be the shorter wavelength region, and this would be the longer wavelength region. On the left side of violet we would have ultraviolet and gamma and X-rays, as we have just seen on the previous page. And on the right hand side of red we would have infrared and radio waves and microwaves and radar waves and all the longer wavelength radiation. So if there is a body at a lower temperature of, let's say, 27 degrees Celsius, 30, 40 degrees Celsius, 20 degrees Celsius, so it would be emitting because emission is related to the temperature of the body. So it would be emitting all the radiation in the infrared band or in the longer wavelength band region. And if we increase the temperature of the body from 300 to 400, 500, 700 and then 800, we are being shown the 800 curve. So what happens when the temperature of the body is increased? You see that the area under this curve has increased, under this 800 Kelvin curve has increased as compared to the area under 300 Kelvin curve. It means that if the temperature of the body is higher, then it will emit more radiations, because the area under the curve is in fact what is the area under the curve? It is integral of y dx. And what do we have on y? Spectral emissive power. It means we are summing up the spectral emissive power, and when we sum up the spectral emissive powers, what do we get? As I just told you on the previous page, if we add up or if we integrate the spectral emissive powers, we get the total emissive power. So the bodies which are at higher temperatures would emit more radiation, and we can see that over here a large area is there. And if the temperature is increased more to 1000 Kelvin to 2000 Kelvin, so therefore the area will keep on increasing. Now, so one thing that we are taking from here is that the bodies which are at lower temperatures would be emitting longer wavelengths, and the bodies which are at very high temperatures would be emitting radiations in visible band and even in the ultraviolet band. For example, this 800 Kelvin body is not emitting anything in the ultraviolet band. However, it is emitting something in the visible band. But this 2000 Kelvin body, is emitting radiation in the ultraviolet band, in the visible band, and in the infrared band as well. So the higher the temperature of the body, broader would be its spectrum. The higher the temperature of the body, broader would be the spectrum of its emitted radiation. This is what we were discussing in the initial slides. Now, let's say we have a piece of iron at 300 Kelvin. Right? And if we have that piece of iron left in a dark room, so would we be able to see it by the radiations, by virtue of the radiations emitted by that piece of iron? What I am trying to say is that if we have a piece of iron which is there in a dark room, so would it be emitting radiations? Of course it would be emitting radiations, because it would be at a temperature of 25, 30, 35 degrees Celsius. So it would certainly be emitting radiations. The question is, would we be able to see that piece of iron by virtue of the radiations emitted by that piece of iron? The answer is no. Why? Because that iron is at a temperature of 25, 30, 35, 40 degrees Celsius. And the bodies which are at this lower temperature would be emitting radiations in the infrared band and beyond. And a human eye cannot see that infrared radiation and beyond without any particular rate. So we would not be able to see that piece of iron by virtue or due to the emissions, by virtue of the radiations emitted by that piece of iron. We would not be able to see that piece of iron. However, if in the same dark room we heat that piece of iron and increase its temperature, and we then leave that piece of iron in the dark, would we be able to see it now? Now you will say that we would be able to see that piece of iron, and it would appear to us red hot. Right? It would appear to us red hot. Why it appears to us red hot? Because it is now at a higher temperature. So even if the room is dark, we will now be able to see that piece of iron, and it will appear red hot to us. See why it would appear red hot to us. Let's say if it is at a temperature of 700 or 800 or 900 Kelvin, what happens is that this curve slowly moves to the left. So from the infrared region, it will enter the visible band from the red portion. So that is why that piece of iron would appear red to us. Why it would appear red to us? Because since its temperature has been increased, it will now start emitting some radiations in the visible band. And what that radiation would be? The radiation corresponding to red color. And that is why it would appear red to us. So by increasing the temperature of the body, we would be able to see the bodies by virtue of the radiations emitted by those bodies. So if this is so, then how do we see the objects around us? How do we see the cars? How do we see the roads, the trees, the tables, chairs? Because all those objects are not at 800 or 700 or 900 Kelvin. They are at normal temperatures of room temperatures of like 20, 25, 30, 35, 40 degrees Celsius. So how do we see those objects? See, if we talk about daytime, then what happens is that the sun would also be out there. And this is the isotherm for sun. So sun is emitting in the ultraviolet band over here. Sun is emitting a part of radiation in the visible band over here, and sun is emitting the radiation in infrared band as well. So out of ultraviolet, visible and infrared, which radiations emitted by the sun would help us in seeing the sun? Of course, the radiations which are being emitted in the visible band, because a human eye can only see the visible band. And since the top of this curve is somewhere near yellow, so that is why the sun appears yellow to us. Now we were discussing that how do we see all the objects around us, since all the objects are at 300 Kelvin or near 300 Kelvin. So the radiations that they are emitting will not help us in seeing the objects at all. So what happens is that during the daytime we have got the sun out there, and the radiations that are being emitted by sun are in the ultraviolet region, visible region, and in the infrared region, etc., etc. So some of those radiations will fall onto, for example, a chair, right? Will fall onto a chair, for example. And depending upon the reflectivity of the surface of the chair, that solar radiation will be reflected off the chair, and that reflected radiation may be in the infrared band or visible band or in the ultraviolet band. So if that chair only reflects ultraviolet radiation, again we will not be able to see the object by virtue of the radiation reflected by that object. If that chair reflects infrared radiation, not emit. See, reflection will be related to incident radiation. And what is that incident radiation? It is that solar radiation which is being incident upon that chair. And now if that chair reflects the infrared radiation, again we will not be able to see the chair due to the radiation reflected in the infrared band, because a human eye cannot see infrared radiation. Only if that chair reflects radiation in the visible band, we would be able to see the chair by virtue of the radiation reflected by the chair. So how do we see the objects around us? We see the objects around us by virtue of the radiations reflected by those objects. Now if the object is reflecting the radiation corresponding to the radiation having wavelength of 0.7 micrometers, so it would appear red to us. Now if that object is reflecting radiation having wavelength of 0.4 micrometers, it would appear violet or bluish to us. If it reflects waves having wavelengths of about 0.5 micrometers, so it would appear yellowish to us or probably greenish to us. And suppose if an object appears black to us, it means that it does not reflect anything in the visible band, so that is why it would appear black to us. And if an object appears white to us, so then it is reflecting all the radiation in the visible band, and that is why it is appearing white to us. If you recall, you used to learn in matriculation mathematics that if you have a piece of paper on which you put all the 7 colors and then you start rotating it, you will not see any color, but you will see white. So if the object is appearing white, it means that it is reflecting all the colors in the visible band, and that is why it appears white. Now this is the same curve from our book, which is figure 12-12 of our book, which defines the same phenomena that we have just discussed over here. So let's discuss 4 points over here regarding those curves. The first one says that the emitted radiation is a function of wavelength. Emitted radiation is a function of wavelength. At a fixed temperature, it increases with lambda. At a fixed temperature, it increases with an increase in lambda, reaches a particular a peak, and then it starts decreasing. At any wavelength, the amount of emitted radiation increases with the increasing temperature. At any wavelength, let's say for example at 4 micrometer. So at 4 micrometers, if we are having a temperature of 300, then this would be the spectral emissive power. However, at 4 micrometer, if the temperature of the body is 800, then it would be having higher spectral emissive power. So at any particular wavelength, the amount of emitted radiation of course increases with increasing temperature. Now as the temperature increases, the curves shift to the left towards the shorter wavelength region. The curves shift towards the left towards the shorter wavelength region. Consequently, a larger fraction of the radiation is emitted at shorter wavelengths at highest temperatures. Of course, at highest temperatures, so there would be, because the peaks would start occurring at shorter wavelengths. The peaks would start occurring at shorter wavelengths. Now the radiation emitted by the sun, which is considered to be a black body at approximately 5800 Kelvin, reaches its peak in the visible region of the spectrum. Thus the sun is in tune with our eyes. We can see it and it appears yellow to us, as discussed before. On the other hand, the surfaces which are at temperatures less than 800 Kelvin emit almost entirely in the infrared region. You can see over here that those bodies which are at temperatures less than 800 Kelvin, they emit the radiations almost entirely in that band that we cannot see, that a human eye cannot see. So it will not be visible to eyes so those objects will not be visible to eyes unless they reflect the light. They reflect the light means they reflect the radiation in the visible band coming from other resources. This is very important discussion that I was telling you on the previous page. So we can see a body by virtue of the radiations emitted by a body or by virtue of the radiations reflected by the body. If we know that there is a body which is at lower temperature, and all the bodies around us are at lower temperatures except hot metal strips or furnaces or things like that. So all those bodies which are at lower temperatures will only be emitting radiations in the infrared band or beyond. So we would not be able to see them because they are emitting radiation in the non-visible band. So we would not be able to see them unless they reflect the light, unless they reflect some of the radiation in this visible band. And where will it come from? From other resources such as sun, or such as tube lights or bulbs or LEDs, things like that. Now over here we can see this law which is called Wein's displacement law, and it says lambda T max is equal to constant, and that constant is 2898 micrometer Kelvin. So what is this thing? See, it says that the product of lambda would remain constant. Now what does this mean? It means that if the body is at lower temperature, its maximum means its peak would occur if the body is at lower temperature, its peak would occur at larger wavelengths. See over here, if the body is at 300 Kelvin, if it is at lower temperature, its peak occurs at larger wavelengths. However, if a body is at higher temperature, let's say 2000 Kelvin, so then its peak would occur at lower wavelengths, such that the product of the two, lambda and T, remains constant, and that constant is 2898 micrometer Kelvin, where micrometer are the units of lambda wavelength and Kelvin are the units of temperature, absolute temperature. This simple expression is Wein's displacement law. So over here we are going to discuss a few more terms. The first one says that the spectral blackbody emissive power over entire wavelength spectrum. This is what we have discussed previously, that if you integrate the spectral emissive power EB lambda over all the wavelengths with respect to lambda from 0 to infinity, where 0 would refer to the minimum wavelength and infinity would refer to the largest wavelength, so that would be equal to the total emissive power means sigma T4. Now it says spectral blackbody emissive power over a wavelength band, not over the entire wavelength, rather over a particular wavelength band from 0 to lambda. So we are interested in finding out this fraction, or this in fact this fraction of the total emissive power. So it is represented as EB 0 to lambda 1. If this is lambda 1, starting from 0 to lambda 1, so what would this fraction be? So that would be the integral of EB lambda from 0 to that particular value of lambda, whether we call it lambda or lambda 1 or lambda dash. Then we have this term which says spectral blackbody emissive power over a wavelength band from lambda 1 to lambda 2. From lambda 1 to lambda 2 means if we have now what would be, why one would be interested in finding this out? First of all, so lambda 1 may be, let's say, 400 nanometers and lambda 2 may be 700 nanometers. So why would someone be interested in finding out? In fact, he would be finding this out as this would be the fraction of the radiation emitted in the visible band, right? Out of the total radiation emitted. Or if someone is interested in finding this area out, this one over here, so this one may be in the ultraviolet region. If lambda 1 is the start, if lambda 1 is, let's say, 400 nanometers, so this one would be ultraviolet and X-ray and gamma rays, means all the shorter wavelength radiations. So, and we can write it in this form: EB from lambda 1 to lambda 2. It is not lambda 1 minus lambda 2, it is lambda 1 to lambda 2, would be integral of EB lambda, whatever this curve is. This curve is for EB lambda, this curve is for EB lambda, from starting point to ending point, from the lower limit to the upper limit. And this fraction, this f between lambda 1 and lambda 2 may be written in this form. It is equal to f0 to lambda 2 minus f0 to lambda 1. So from 0 to lambda 2, this is total fraction, minus 0 to lambda 1, this total fraction. The difference of the two will give us what is the shaded portion. So in fact, probably you would have done this thing in for example statistics and probability problems, especially in normal distribution problems. So that is the same thing, that is the same way we would be finding this fraction out. Now f0 to lambda can be written in this form. It is integral of EB lambda over the entire, means integral of the same EB lambda but from 0 to infinity, means over all wavelengths, and the denominator is equal to sigma T4 as is written over here. The denominator, if you integrate the spectral emissive power over all the wavelengths, it will give us total emissive power means sigma T4, and the numerator remains unchanged. Now this fraction may be written in this form. It is integral of emissive power, spectral emissive power from 0 to lambda 2 minus integral of emissive power from 0 to lambda 1, means 0 to lambda 2 minus 0 to lambda 1 over the total. So this thing over sigma T4 will be f0 to lambda 2, fraction 0 to lambda 2, and this thing over sigma T4 would be fraction 0 to lambda 1. So that is the same thing that we have just discussed at this step. So the integral of this under the area of this curve, what is this curve? It is between lambda wavelength and the EB lambda, means the spectral emissive power. So this equation would be a function of See, if we have this over here y and if we have x over here, so this curve would be relating y with x. So this curve would be a function relating spectral emissive power with the wavelength or wavelengths, and the area under the curve would give us the total radiation energy emitted at that particular temperature. Now over here, before we go on to solve a problem on this fraction topic that we have just discussed a couple of slides ago, let's have a look at some of the spectral quantities. What is meant by spectral quantities? See, first of all, what does it say over here? We have got lambda over here and we have got I lambda E over here. And it says that this is the sort of curve which would be actual curve, and it would not be such a smooth curve. In reality, we get such wavy types of curves which approximate, they can be approximated all the time. And the integration of a spectral quantity means any quantity which varies with wavelength, so integration of a spectral quantity for all the wavelengths gives what? Gives the total quantity. For example, integration of spectral emissive power will give us total emissive power. And over here it shows approximating the actual variation of emissivity with wavelength by a step function. So one important thing over here is that you can see that what do we have on x-axis is the wavelength, and what do we have on y-axis is the emissivity. So over here it is a very important diagram, and I have brought it for a particular purpose. In fact, this diagram is telling us that this particular body, whatever that body is, whatever that object is, has got an emissivity equal to epsilon 1 in the wavelength band 0 to lambda 1. And then that body has got an emissivity value equal to epsilon 2 in the wavelength band lambda 1 to lambda 2. And then the same object has got an emissivity equal to epsilon 3 for wavelengths of lambda 2 and greater. So an important message is that epsilon, which is the emissivity, is not a constant quantity. We most of the times take it as a constant value, but it really varies with the wavelength. So whether it is emissivity or whether it is absorptivity or reflectivity or transmissivity, they all are not constant quantities, rather they vary with different wavelengths. For example, let me ask you a very simple question. If I ask you that is glass transparent or opaque? Glass is transparent or opaque? Of course you will reply that it is transparent. And why would you call it transparent? Because you can see the other side of the glass, or you can say that the light passes through this glass, and that is fine to a certain extent. And if I ask you, what about the wall? Is wall transparent or opaque? Then you will say that wall is opaque. And if I ask you the reason, you will say that we cannot see on the other side of the wall, and of course it means that the light cannot pass onto the other side of the wall, and that is why it is opaque. See, what is light? Light is radiation, right? Light is radiation in the visible band having wavelengths of 400 nanometers to 700 nanometers. So if the wall is opaque, that means that the radiation having wavelengths of 400 nanometer to 700 nanometer cannot penetrate into the wall, cannot go on the other side of the wall, right? And that is completely true. But do you think that the same stands true for gamma rays? Do you think that the wall of any house or any building can stop the gamma rays? Of course not. The gamma rays or any other very short wavelength radiation would certainly penetrate the wall, and it will go on the other side of the wall. So the wall will be opaque for 400 to 700 nanometer radiation. The wall will be called opaque for visible light radiation, but it will be transparent for example, gamma radiation. So its transmissivity is wavelength dependent. Its transmissivity is dependent upon lambda. Its transmissivity is not a constant value. For shorter wavelengths, it will have a higher transmissivity value, and for medium or larger wavelengths, it would then have a lower transmissivity value. Right? So whether it is transmissivity or reflectivity or emissivity, those things are in fact dependent upon the wavelengths, and therefore they are spectral quantities. Now let's take a problem. We have to find out the fraction of the radiation emitted by sun in visible band. Emitted by the sun in the visible band. So now let's say if this is the visible band. Right? This is the figure that we were talking about a couple of slides earlier. And let's say lambda 1 is 400 nanometers and lambda 2 is 700 nanometers. Or some people take it as 380 nanometers to 740 nanometers, that is fine. So we are trying to learn how to find that out. So f lambda 1 to lambda 2 would be f0 to lambda 2 minus f0 to lambda 1. F lambda 1 to lambda 2 means f in the this f would be the fraction of radiation emitted by sun in the visible band, which has been shown over here. So that would be f0 to lambda 2, means we will find out f is starting from 0 to lambda 2, and then we will try to find out f0 to lambda 1, and we will take the difference of the two. The difference between the two will be the required area, the required fraction. Now in order to find that out, we have this table which is 12.2 of our book, black body radiation functions, in which we are given this value of f starting from 0. So since in order to use this table the fraction must start from 0, that is why we converted all the things in the fractions that have a starting point of 0. And we can read out the values of f once we know the values of lambda t in micrometer Kelvin. So we must have lambda wavelength in micrometers, and we must have temperatures in Kelvin. So we will read out the value of f against the values of lambda t. So it is this table, and it starts with 200 and then goes beyond to large values. So going back to the problem. So therefore we will find lambda 1t and lambda 2t. Lambda 1 is 0.4 micrometers. We in order to use that table, the units of wavelength must be micrometers. So 0.4 micrometers times 5800 Kelvin, as discussed, is the temperature of the sun, and similarly lambda 2 is 0.7. So this will be about 2320 micrometers Kelvin, and this would be about 4060 micrometers Kelvin. So 2320 and 4060. Now at 2320, at 2200 this fraction is 10%, and at 2400 micrometer Kelvin this fraction is 14%, 0.14. So at about 2300 that would be near 12%, or just more than 12%. So we can take it as 0.2. So that fraction would be 0.2 at 2320. So at 2320 means f0 to lambda 1t, f0 to lambda 1t, this fraction is 0.12. For the next one, where lambda 2t is 4060, so at 4000 this fraction is 0.48, and at 4200 this fraction is 0.51. So if you interpolate, so you will get the value of about 0.49 at 4060. Now at 0.49. So therefore, 0.49 minus 0.2 will give us 0.37. Again, that depends upon upon values that we have taken as 0.4 micrometers and 0.7 micrometers. If someone takes a little bit different values of 0.38 and 0.72, so this fraction will increase by a little amount. So it is 37%. Now what does this 37% mean? It means that the sun emits 37% in the visible band. Sun emits 37% of total radiation in the visible band. So if someone asks you that how much is up till ultraviolet band, so of course that would be 0.12, because this portion is 12%, right? So this is how we can find the fraction of radiation emitted by any object, not only sun. For example, if you take a look at couple of problems in the book, you will find that they have worked the things out where they have found out the fractions of radiation emitted by a particular object which is at, for example, 800 Kelvin. So all you need to do is multiply that lambda by that temperature and simply read out the values of the fraction from the table. This is how simple that is. Now the Kirchhoff's law. Kirchhoff's law says that if we have a small body, this is the small body which is placed in a large enclosure. So if this is a small body having a surface area of AS, having an emissivity of epsilon, it means that this body is gray, because the emissivity of black body would be 1, and having an absorptivity of alpha, and it is at a temperature T, and it is contained in a large isothermal enclosure. So this whole large isothermal enclosure is isothermal, means it would be at temperature T. The whole surface would be at the same temperature, so that is why it would be isothermal, and such that they both are at same temperatures, means they both are in thermal equilibrium. So the large isothermal enclosure would approximate the behavior of black body, as discussed before in chapter number 1, because whenever a radiation would come in, so it will get absorbed after multiple reflections. Because let's say a radiation comes in having a magnitude of 10. Suppose that 3 gets absorbed and 7 gets reflected. So upon the second hit, another 3 will get absorbed and 4 will get reflected, and on the third hit another 3 will get absorbed and only 1 will be reflected, which will get absorbed in the fourth hit. So if it is a large enclosure or large body or large furnace or large room or large surroundings, so they approximate the behavior of black body in being perfect absorbers. So now if the radiation incident on any part of the surface of the small body would be equal to the radiation emitted by the black body. By the black body means by the large enclosure at temperature T. It means that if the two bodies are in equilibrium, then the body, means the small body, will emit as much radiation as it absorbs, right? Because if it absorbs more than what it emits, so then its temperature will keep on increasing, and if it emits more than what it is receiving, so its energy content will start decreasing. So if they are in thermal equilibrium, it means that this small body will gain as much as it loses. It means that it will absorb as much as it emits. So how much? So E would be equal to alpha G. What is E? The amount of radiation which is being emitted by the small body. And what is alpha G? Alpha G is the amount of radiation which is being absorbed by this small body. And why it is alpha G? See, G would be the radiation incident upon it. G would be the radiation incident upon it from the large enclosure, right? And will it absorb all of it? No. Why? Because it is not a perfect absorber. It is not a black body. So it will not absorb all the incident radiation. See, only Only a black body is a perfect absorber by definition. So in fact alpha absorptivity would be 1 or 100% for a black body, and for any other real body or gray surface its value would be less than 1. So how much would it absorb? It will absorb alpha g. Why alpha g? Because g would be the radiation that would be incident upon this small object, and it will be multiplied with its absorptivity, which is alpha. Now E would be sigma epsilon T4, and it is not sigma T4 because E is the radiation emitted by the small body, and a small body is not black, right? It is the large enclosure which behaves like a black body, but the small body does not behave like a black body. So therefore its emissive power would be epsilon sigma T4. Alpha remains alpha, and G is the radiation emitted by the large enclosure, which would be sigma T4. So sigma T4 will get cancelled out, and we will get that epsilon is equal to alpha. This simple expression is Kirchhoff law. Now greenhouse effect. Greenhouse effect is in fact the entrapment of radiation. And let me give you a simple example of a car. Let's say you are coming to the campus, or you are going anywhere. Let's say you are coming to the campus, and you park your car at a place, and you go for a certain piece of work. But when you come back after, let's say, 20 or 30 minutes, and when you sit inside the car, we find that the inside of the car is at a much elevated temperature as compared to the outside air temperature. Outside air temperature may be like 30-35 degrees Celsius, but inside the car we find it to be a lot more, probably approaching 40, 42, 43 degrees Celsius, a lot more. So what happens is that, see, and when does it happen? When we park it in the sun, right? If we park in a shadow, we do not feel it that hot, or it does not happen during night time. So what happens is that when the sun is out there, now the sun is emitting radiations, and as per Wein's displacement law, lambda T max is equal to constant. The temperature is the temperature of the sun is very high. As we just discussed, we take it as around 5800 Kelvin. So therefore a lot of radiation would be shorter wavelength radiation. Or the peak would occur at shorter wavelength radiation. You can refer back to that spectral emissive power curve. So what will happen is that those shorter wavelength radiation will pass through the glass. That shorter wavelength radiation will pass through the glass, and it will go inside. Why does this happen? It happens because the glass, kindly listen it very carefully, because the glass is transparent for shorter wavelength radiation. Means the glass will let all the shorter wavelength radiation pass through it. Now what is happening inside the car? Inside the car there are seats, there is dashboard, there is carpet, there are all such things, steering, etc., etc. And those objects are at lower temperatures as compared to the temperature of the sun. They would be at 35, 40, 42, 43, 45, 46 degrees Celsius. So they would also be emitting radiations, because any body whose temperature is above 0 Kelvin emits radiations. But since those objects which are inside the car are at lower temperatures as compared to sun, they would be emitting radiations of larger wavelengths. Again, lambda T max is equal to constant. If lambda T max has to remain constant, and if T is less, then lambda would be more. So more of the radiations would be of longer wavelength. And those longer wavelength radiation would be emitted by the carpet, by the dashboard, by the seats, etc., 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 by the steering and all that. And a peculiar property of glass is that it is opaque for longer wavelength radiation. Means that the glass will not let the longer wavelength radiation pass through it. So again, if I make this phenomena, If I draw this phenomena, means if on x-axis we have got lambda wavelength, and over here we have got transmissivity, tau, transmissivity of the glass, then what is happening is that for shorter wavelength radiation, the glass is highly transparent, means that it is highly transmissive. So its transmissivity is higher for shorter wavelength radiation. It is letting all the shorter wavelength pass through it. But for longer wavelength radiation, the glass becomes opaque, means it does not let the longer wavelength radiation pass through it. So for longer wavelength radiation, its transmissivity is very low. So again, as we were discussing before, transmissivity is also wavelength dependent. Transmissivity is also wavelength dependent. So what happens? What happens in the end? The radiations start accumulating inside the car. The radiations start accumulating inside the car, due to which the temperature of the inside of the car rises. This effect of entrapment of the radiation is called greenhouse effect. Now we usually use the greenhouse effect in this sense, right? So what happens? It is the same phenomena. The majority of the wavelengths coming from the sun is of shorter wavelength. The majority of the radiation coming from the sun is of shorter wavelength, and near around the sun, near around the earth, all the objects are at lower temperatures, relatively lower temperatures than the sun. So they would be emitting radiation of longer wavelength. So that longer wavelength radiation will not be able to escape that ozone layer, and all the shorter wavelength radiation will pass through it. So what will happen is that the radiation will get trapped, and therefore the phenomena of what we call the global warming occurs. So in fact, greenhouse effect is in fact the entrapment of radiations wherever it takes place. For example, let me tell you a very interesting fact, that greenhouse effect takes place in solar water heaters. That is not the point under discussion, but it happens over there as well. So let's take one more problem from chapter number 12. It says that the spectral distribution of the radiation, means the distribution of the radiation with respect to the wavelength. So what we can see over here on the x-axis is lambda, and what do we have on the y-axis is E lambda, means spectral emissive power. Again having the same units of watts per square meter per micrometer per unit wavelength. The spectral emissive power of the radiation emitted by a diffuse surface may be approximated as follows. What is a diffuse surface? See, a diffuse surface is one which emits the radiations uniformly in all the directions. For example, if I try to draw it over here, if this is the surface, what happens in reality is that the radiation may leave, more radiation may leave in one particular direction than other directions. So this is not a diffuse surface. A diffuse surface is one. In fact, this happens due to the oppression and depression on the surface of the surface, right? What is a diffuse surface? Diffuse surface is one which emits the radiations uniformly in all the directions. This is a diffuse surface. So we are given the chart for spectral emissive power with respect to wavelength, and we need to find out the total emissive power. So what is the total emissive power? Total emissive power, as we have seen before, is the integral of E lambda with respect to lambda over entire wavelength band, means 0 to infinity. So over here, what is this curve telling us? This curve is telling us that in the wavelength band of 0 to 5, its emissive power is 0, means that it is not emitting anything. It is this object, this surface is not emitting anything, is not emitting any radiation which has a wavelength of 0 to 5 micrometers. So whatever this object is emitting is 5 micrometers and beyond. In fact, 5 to 20. It is between 5 to 10, its emissive power is 100 watts per square meter per micrometer. Between 10 and 15 micrometers, it is emitting the most. 200 watts per square per meter square per micrometer. And then 15 to 20 it drops back again to 100, and from 20 onwards, means from 20 to 30 to 50 to infinity or whatever, its emissive power is again 0. So what we need to do is add up the emissive powers in region 1, in region 2, in region 3, in region 4, and in region 5. In fact 1 and 5 are 0. So integral of E lambda d lambda between 0 to 5, and then 5 to 10, and then 10 to 15, and then 15 through 20, and then 20 through end. So what is the value of E lambda in the band 0 to 5? It is 0. So integral of this thing would be 0. So this thing will not exist. The value of E lambda in the band 5 to 10 has a constant value. It is 100. It could have been 100 times lambda, right? So we would then had to integrate lambda, which would have been equal to lambda square by 2. So wherever it is lambda only, and then 200 in 10 to 15 band, and then in 15 to 20 band it is again 100, and then in the last band it is again 0. So this would not exist as well. So 100 would be taken out of the integral sign, and integral of d lambda would be equal to lambda, and when we place the values of the upper and lower limits of lambda, we get 10 minus 5. Similarly 200 times 15 minus 10, and then 100 times 20 minus 15. At the end we get 2000 watts per square meter. So this is the total emissive power, means this is the total radiation, magnitude of the radiation being emitted by this particular body. Now if I ask you that by looking at the spectral emissive power curve, can you say anything about the temperature of the body? Can you say anything about the temperature of the body? See, whatever it is emitting is in the range of 5 meters and beyond, 5 micrometers and beyond, and 5 micrometers is infrared and beyond. So it means that it is not, because 400 to 700 means 0.4 to 0.7 micrometers is the visible band. So it is not it is not emitting anything in the visible band, and it is not emitting anything in the ultraviolet region as well. So whatever this body is emitting is in the infrared region and beyond. So this body would be might be at lower temperatures, because it is not emitting light, and it is not emitting ultraviolet or gamma rays or X-rays.